NASA Voyager 1 spacecraft, which currently holds the record for the most distant object ever constructed by humans, has fascinated individuals worldwide for almost 5 decades since its launch. Voyager 1 has transmitted vital data from the farthest reaches of outer space, improving humanity's understanding of the universe. However, recent transmissions from the probe have exhibited unusual anomalies and have left specialists perplexed. These enigmatic signals have ignited intense discussions, prompting the scientific community to question whether these inconsistencies are merely technical malfunctions or signs of something far more unusual, possibly even involvement from extraterrestrials. Join us as we explore these perplexing messages and investigate what may be concealed within the vast expanse of the cosmos. The intrinsic human desire to uncover mysteries has long driven our quest for the exploration of space. This profound curiosity paved the way for ambitious projects such as Pioneer 10 and Pioneer 11, which were among the most daring space missions of their era. On August 20, 1977, the launch of Voyager 2 from NASA Kennedy Space Center marked the beginning of a groundbreaking era in space exploration. Shortly thereafter, on September 5, 1977, Voyager 1 was dispatched into space, embarking on a journey that would lead it to the outer planets, dramatically altering its trajectory and the results of scientific research. Each probe, with an approximate mass of 721 kilograms, about the size of a small car, traveled in distinct directions at a variety of speeds. On December 15, 1977, an important milestone was reached when Voyager 1 surpassed its twin in terms of the total distance traveled along their divergent routes. Since then, Voyager 1 has served as a crucial asset in deepening our perception of space, presenting findings that have transformed our understanding of the universe. Before delving into some of its recent groundbreaking findings, let's revisit several of its earlier key accomplishments. In 1979, positioned roughly 265 million kilometers from Earth, Voyager 1 captured high-resolution images of Jupiter. By January of that year, it had logged a respectable 100 hours of study, resulting in a time-lapse sequence that depicted Jupiter's rotation. This set of 3,750 images provided unprecedented insights into the planet's turbulent atmosphere and complex features. While on this mission, Voyager 1 also detected a previously unidentified ring around Jupiter and discovered 2 unknown moons, significantly enhancing our knowledge of the gas giant's intricate system. To maintain its course and avoid colliding with Titan, one of Saturn's moons, the probe carried out a number of navigation modifications. Subsequently, the mission focused on something beyond the planets, as the spacecraft was redirected into interstellar space, traveling at an extraordinary pace of 325 million kilometers annually. In January 1990, Voyager 1 commenced its assignment to explore interstellar space, pressing onward beyond the boundaries of our solar system. During this phase, it completed numerous exceptional feats, such as identifying new moons including Mimas, Enceladus, Tethys, and Rhea, while capturing some of the most memorable images of the solar system's outer boundaries. On February 14, 1990, from a distance of nearly 6 billion kilometers from the Sun, Voyager 1 captured the iconic family portrait, a panoramic collection of images of the inner planets. This compilation of 60 pictures was added to the probe's extensive gallery, which already featured hundreds of images from its close encounters with the gas giants. Voyager 2, in parallel, achieved remarkable milestones during its journey. Wind speeds measured on Neptune exceeded 2,100 kilometers per hour, making them the fastest atmospheric currents ever recorded in the solar system. It also observed Triton, Neptune's largest moon, where temperatures dropped to nearly negative 391 degrees Fahrenheit, negative 235 degrees Celsius, ranking it among the coldest known locations. Triton showed evidence of icy eruptions that released nitrogen gas and frozen debris up to 5 kilometers high, revealing fascinating new aspects of its geology. These extraordinary discoveries significantly broadened our comprehension of the numerous and dynamic conditions in regions beyond the solar system. The effects of Voyager 1 and Voyager 2 have been truly transformative. Their results revealed previously concealed characteristics of Jupiter and Saturn's moons. Once thought to be inactive, this new evidence altered beliefs regarding their geological activity. Voyager 2, in particular, made history as the only spacecraft to date to pass close to both Uranus and Neptune, an unparalleled achievement. NASA utilized a number of novel methods for extending the lives of these groundbreaking missions, such as powering down non-essential components to reduce energy use. The mission is projected to continue until 2030, symbolizing the conclusion of a remarkable chapter for the teams who dedicated themselves to it. The construction of Voyager 1 and Voyager 2 exemplified advanced design and engineering. Built to rotate slowly, these probes minimize motion blur in their images during travel. Even before arriving at the outer planets, the spacecraft began relaying detailed visuals of Jupiter, unveiling its whirling clouds and the well-known Great Red Spot, a massive storm that has piqued scientists' interest for decades. One of the most exciting findings was the detection of active volcanoes on Io. Equipment on board the spacecraft recorded strange readings from the moon, later validated by images showing huge volcanic plumes and a violently reshaped surface. One eruption on Io was found to be 1,000 times as powerful as eruptions from Mount St. Helens, which covered an area that was nearly the dimension of France. As their voyages continued, the two spacecraft gradually powered down to save fuel before heading into interstellar space. Surprisingly, they did not take any pictures of Mercury or Mars due to technical constraints. NASA later launched additional significant missions, including Pioneer 10, Pioneer 11, and New Horizons. On February 17, 1998, Pioneer 10 surpassed Pioneer 11 to become the most distant probe from Earth. Nevertheless, Voyager 1 continued it traveled for an additional 14 years before officially entering interstellar space on August 25, 2012. A pivotal factor in the triumph of these missions was the strategic utilization of gravitational slingshot maneuvers, which propelled the spacecraft toward their objectives while conserving fuel. Rather than depending entirely on propulsion systems, they made use of the planet's gravity to increase their speed and alter course. This technique enabled them to span colossal distances with minimal fuel expenditure. As Voyager 1 approached Jupiter, Jupiter's massive gravity accelerated the spacecraft. Precision was essential to avoid hazardous changes in speed or trajectory. These gravitational boosts allowed the probes to expertly traverse the solar system. Voyager 2 likewise exploited gravitational pulls from Jupiter and Saturn to propel itself toward Uranus and Neptune, validating how well this navigation method worked. Considering these extraordinary undertakings, the scientific community anticipates further insights from the anomalous transmissions recently detected by Voyager 1. These spacecraft continue functioning far beyond the solar system's known perimeter, probing the mysteries of planets like Jupiter, Saturn, Uranus, and Neptune. The time-lapse sequences from Voyager 1 vividly documented eruptions on Jupiter and revealed new satellites, as well as a previously unrecognized ring encircling the planet. These revelations significantly enriched our comprehension of the Jovian system. Similarly, Voyager 1 discovered 4 additional moons orbiting Saturn: Mimas, Rhea, Enceladus, and Tethys, in addition to providing breathtaking visuals of the planet and its rings with their illuminated and elaborate structures. The mission's expeditions to Uranus and Neptune made important observations about their atmospheres and satellites, enhancing our grasp of the solar system's distant territories. After finishing their planetary flybys, both probes set course for interstellar space, where they continue collecting important scientific data. This ongoing investigation widens our perspective on what lies beyond our solar system's neighborhood. While we wait for new developments pertaining to Voyager 1's peculiar emissions and their implications for our understanding of the cosmos, the incredible journeys of these probes continue to inspire both researchers and enthusiasts globally. Their accomplishments remain foundational in expanding human knowledge and pushing the limits of space science. The Voyager initiatives have delivered unprecedented glimpses of regions far beyond our solar system, offering iconic imagery and valuable scientific results. In addition to their empirical contributions, they have made significant contributions to the field of physics. The spacecraft carry a symbolic artifact, a message crafted to represent Earth to potential extraterrestrial civilizations. The Golden Record contains greetings in 55 languages, musical pieces from various cultures, and natural sounds such as whale songs and thunder. This interstellar communication serves as humanity's hopeful attempt to connect with intelligent life beyond Earth. Both Voyager 1 and Voyager 2 were equipped with an array of scientific instruments that significantly enhanced our comprehension of space. These included magnetometers, plasma wave sensors, and imaging tools, all of which supplied critical data about space environments. The magnetometers deciphered the magnetic fields of Jupiter, Saturn, Neptune, and Uranus, demonstrating how these fields interact with their surroundings. Plasma wave detectors clarified the impact of solar wind on planetary atmospheres. One of the mission's standout accomplishments was tracing the boundary of the heliosphere, a vast region populated by particles and electromagnetic fields from the Sun that envelops our solar system. As Voyager 1 approached this boundary, it observed the transition from solar wind to interstellar material, resulting in essential insights into how this barrier protects Earth from cosmic rays. The spacecraft also located a region known as the termination shock, where solar winds condense and slow down. Beyond it, that lies the turbulent heliosheath, a region where solar and interstellar particles collide, creating a dynamic environment. Voyager 2's expedition also greatly enhanced our comprehension of the outer solar system. Its quick passes by the giant planets offered critical observations, particularly regarding the magnetic field of Uranus, which was discovered to lean in an unexpected direction that defied existing theories. These findings sparked additional research into planetary magnetism. These endeavors not only advanced scientific insight, but also rekindled public fascination with space exploration. The mesmerizing images of distant planets and the captivating stories behind these missions have inspired countless individuals across generations. Iconic images, like Saturn's opulent rings and Jupiter's volcanic moons, have become exemplary inspirations for young scientists and aspiring explorers. As the Voyager spacecraft persists in transmitting outstanding information, their extended exploration of interstellar realms offers unmatched opportunities to decipher the fundamental nature of the universe. Despite prior emphasis frequently being placed on planetary exploration within the solar system, interstellar space has shown unexpected complexity. Zones once presumed empty are now recognized as displaying intricate phenomena that challenge current scientific paradigms. Among the most captivating findings is the discovery of cosmic rays originating from beyond our solar system. These highly energized particles, traveling nearly at the speed of light, provide clues about processes occurring in remote parts of the galaxy. By examining the energy levels and composition, scientists aim to better comprehend the dynamics of distant stellar nurseries and galactic behavior. Additionally, as Voyager 1 and Voyager 2 delve deeper into interstellar territory, their onboard instruments continue to evaluate the density and movement of the interstellar medium, the diffuse matter, that occupies space between stars. This medium, composed of gas and dust, interacts with the solar wind and shapes the heliosphere's configuration. As the probes navigate through it, they relay important information that helps researchers model how energy and matter operate across cosmic distances. In addition to these accomplishments, the Voyager missions have unveiled essential details about magnetic fields in interstellar space, shedding light on their properties and influence. These revelations could eventually drive breakthroughs in understanding magnetic forces throughout the galaxy. The ongoing exploration of these distant frontiers not only extends our scientific awareness, but also motivates future generations of space scientists and engineers. The unforgettable images gathered by Voyager, particularly the renowned pale blue dot photograph showing Earth from over 6 billion kilometers away, serve as a humbling reminder of our tiny presence in the cosmos. These snapshots, combined with the mission's scientific accomplishments, have deeply reshaped how we perceive our world and its position in existence. The success of the Voyager mission set the stage for even more daring endeavors. Thanks to the advancements developed during their expeditions, launching sophisticated probes to more remote corners of the galaxy is becoming increasingly achievable. Ambitions such as exploring exoplanets, identifying potentially habitable worlds, and even interstellar travel are gradually evolving from visionary concepts into practical objectives for a future of cosmic discovery.